everybody for attending. So yeah, thank you so much. Thank you everybody for attending. I'm very happy to introduce some results from my previous research and my views from many years of passion and interest in this special cross-discipline topic of ancient water technologies. Myself, as you heard before, I'm a civil hydraulic engineer. My background is civil engineering. And since my latest years in the university, as a undergraduate degree, I got passionate about Roman ancient structures and how sturdy they were and how brilliantly they survived millions or thousands of years, and they are still standing and operating efficiently. In some cases, they were reused and still there. I was therefore starting an independent researcher, looking for information, going around university libraries in Italy a long time before the internet existed. So just physically drawing into the archives. It was just my own interest, and I gradually built up a bit of information. And although, of course, when you go on your own, it's a lot less you can achieve compared to academic possibilities. So I'm now very happy that finally, after more than 15 years, I started more than 3 years ago, this PhD exploring the water system in Pompei in Northumbria University. And I'm now tonight presenting some perspective for water engineering. What else can be done? How engineering can produce information for archaeology, and what engineers are looking to find out when exploring ancient water system. So the main objective, the main topics will be how hydraulic analysis will contribute to the current understanding of the ancient technologies. What data do we need to perform some calculations? What basic data is needed? And finally, some information that I deducted from the water system of Pompei, looking at public fountains. So water engineering is an ancient practice, and we definitely know that any civilization had to provide and look for water sources and resources. Water storage and running water were a daily need, and they were all addressed in ancient civilization. The main principle were the natural forces and basically gravity. So the main good point of all ancient systems is that they an interlocked network of basins. They are located in various levels and various locations, connected by other elements. So that some flow rate regulation is achieved, and pressure regulation. So the very good point of this system that with very little means and using the gravity forces, they were achieving what in nowadays engineering we achieve with a lot more effort and structural resources and other energy resources. So there's definitely a point in looking at ancient system as energy efficient, radicated into local customs, many cases well integrated in the environment. So there's a lot of interest for modern engineering in discovering the practices of ancient engineers. Although the system, they might look quite simple at a first glance, they're not as such, because the more we investigate into the ancient structure, the more we find out that some issues which also nowadays we need to address in modern water engineering, they were already addressed. So basically any type of storage or distribution of water had to deal with the sanitation of the water and keeping the water quality, so avoiding the growth of pathogenic bacteria, contamination. Also, any elements like channels and pipes, they had to be designed to avoid the excessive flow rates, so the excessive discharges of water, so that the precious resource of water was, delivered in the right time and when it was needed, and was stored when it needed to be stored. So that's also quite interesting, as many engineers, they have been discussing the efficiency of the transport of the water into these transport elements. And of course, water was not only potable quality, and it's so interesting to look at the use and reuse of water, these patterns in town, in other environments like agricultural areas and industrial settings. So all of these patterns, they need to be explored, and nowadays there's so many studies that they are addressing these features. We now might look better at the Roman water distribution system, which is more my topic. What other scholars have suggested to progress this research, and what are the published hydraulic studies? Looking at, oh my God, sorry, there's a telephone running. My fault. Should mute my phone. I didn't. I'm sorry, I apologize. So it was since in 1991 that already Trevor Hodge, which wrote that good, well-known reference book on the Roman aqueducts and Roman water system, outlined how engineers could support knowledge on of ancient structure and provide new information for archaeologists. In 2001, there was a collection of articles and the editor was Colostra Stroh, and she outlined the necessity of more interdisciplinary studies. And in the same book, Wilson suggested how the analysis should approach the entire water cycle, and definitely find out what were the different technology used in various areas of the Roman Empire, because at the beginning there was an attitude of trying to set up a common water system, same for any town and any city. But of course, there's so many studies already published now, and we already know that any system it would be adapted to the local situation, the local practices, and the local hydrology. So any the system have to be differentiated by the different areas. In 2012, Richard was investigating monumental fountains, and he definitely outlined the issues to understand exactly what was the use and the management of water in such impressive fountains like those of the Roman East or in North Africa. They contain so many chambers, so many basins at different levels, and there's patterns of reuse of water, distribution tanks, so there's so much to be yet identified. The published study can be grouped by structure. I identified these groups. These groups are basically those studied addressing the discharge of extra-urban aqueducts. These studies are the majority of the existing numerical studies, because of course traditionally engineers I'm a woman engineer. I don't know, maybe men engineers, they were more impressed by the majestic arches and of the aqueduct channels. Of course, that was is the most striking structure that you're likely to appreciate of Roman aqueducts. But also recently there's been various studies on small system like pipes and tanks, some pipe tanks and channels. And I noted just some of them, like those one from Ephesus, Petra, Priene, I still noted down there, and they're all based on a mixture of computer fluid dynamics and just general hydraulic considerations. The analysis of the supply of some decorative fountains, there's few studies on that, and the analysis of culverts and drop shafts, again, quite limited studies, and the analysis of transporting elements. Basically, the only existing studies are on ceramic pipes, but there's nothing recently published on lead pipe, and we just started some research in Northumbria University. So to conclude from all this little review of the published study, is quite interesting what Charles Ortolov said. Charles Ortolov wrote various a book on a review of different water structure and his analysis, like numerical analysis of some structure in Nabatean and Roman. And recently there's an article, this quote is from this written article on an interpretation of the Castellum in Nîmes. So Charles Ortolov outlined that archaeological literature exists for sure in the last 15 years. So many studies have been published on whatever structures, details of the Roman water system, but what is missing is still a very good knowledge of the engineering, underlying engineering principle on which those structures operated and really functioning. So ideally, there's a lot of details, but still what is missing is the collating those details in a proper engineering interpretation. Roman water structure. So what else can be discovered by applying, this type of analysis like engineering and CFD analysis? Definitely, the water collection structure is a very interesting since they come in so many different layouts. If you think about cisterns, so like structure below ground, collecting rainwater or aqueduct water, they're quite known cistern with many parallel chambers, those other cisterns with just a few compartments, cisterns with just many pillars and columns, like the basilica cisterns. Of course, all those retaining structure, they serve for different uses, but what could be studied is would benefit of a fluid dynamic software and analysis. So what is possible to understand is the distribution of the velocity in the different areas of the structure, and therefore understand which area were more dedicated to settling, and in fact what was the function of the compartments, because one, my personal understanding, and I would love to start this research soon, is that the water was meant to be in slow motion, but going through compartment to assure some degree of aeration. So I'm looking at these tanks more like tanks in a waste or water treatment plant. Like it's a structure in which not just settling is involved, that also aeration could support the presence of dissolved oxygen, which in the water treatment, basics means that you have possibility to oxidate organic matter, which means maintaining some water quality, because basically the presence of solids and organic matter that would cause biological deterioration of the water quality. Definitely, this is something to be better explored, and yeah, definitely computer fluid dynamics is one of the possible methods. This other research is quite interesting, and we just started in Northampton University. There's an article to come soon from my supervisor, which is Professor Martin Krapper, and we were so happy to test 3 stretches of pipes from a bathhouse in Corbridge, near the Adrian, along the Adrian Wall, and the pipes, we were so curious. We investigated through endoscopy, and we were trying to develop a way to understand what was the hydraulic roughness of the pipe, because the problem with us engineer, if we want to calculate a network which is built with lead pipes, we face a problem to assign a value of the roughness. Roughness is restraining the water motion, so the value you assign to the roughness is so crucial to the final results. And the ancient pipe, they're so different from the Roman pipes. So even looking at the shape, if you think like they have the teardrop shape is so different as on the looking at the effects on the water velocity from the circular shape of the cross section. So all these precise measurements can be done only with lab tests. So we had the chance to start with 3 stretches, and unfortunately, if you don't test many pipes, you cannot come to an average conclusion, because this pipe, for example, was very rough. You can see also in the picture how large were these masses, like lump masses in the soldering bed. So that those for sure have quite an effect on the motion of the water inside the pipe and the friction losses. So the method that we applied was to reproduce the surface of the pipe through dental putty, and then scan the dental putty with a 3D microscope, and go with some surface analysis. And we're just testing a method, and in the future, one perspective study is to apply the method to various range of pipes, and also to acquire information through 3D scanning. So it's a technology we don't yet have, it's not as common nowadays. We don't yet have in Northampton University. It's just a long probe that you can insert in the pipe and provide some 3D scanning, so that will help to reconstruct a model of the pipe, and just experiment also through modeling. So there's quite some advances that can be done, but this information is quite crucial, as I said, for developing an understanding of the behavior of the Roman pipes. So looking at more general picture, what data would be better to record to support the engineering analysis? Because what happens is you read all these reports from different professionals of various backgrounds, and for example, looking at lead pipes, sometimes there is mention of the diameters of the pipe, sometimes of the perimeter, but sometimes there's not as much information. There's a lot of reports limiting to say that some pipe have been found, or maybe they assign to the pipe the from frontinus denomination, like quinaria, denaria, without much detail. So for any structure, again, there's lots of reports that this should include a lot more of information. So I'm just now outlining some issues. Of course, when we talk about measurements, we want to understand also the the error associated. The point is, especially when it comes to small tanks or small basin, of course, you wouldn't use very advanced technology like total station triangulation. You will just use more, basic instrumentation. But still, in a lot of reports, there's not much information about how that information, that measurements has been taken, and with which instrument, or mention about the error that was expected, more details about the process. So all of that has to be included, because the problem is that, of course, with archaeology, to have a data which is like 10.5 meter, and that data maybe in archaeology just used for comparison. I mean, if you have 10.5 or 10.55 or 10.60, wouldn't affect as much, because mostly the size is used for comparison between different structures. And of course, it's more discussion, but when it comes to engineering, and use those measurements as an input into some calculation, and so not just one step calculation, but different steps, of course, the error is going to propagate, and of course, affect the final error on the results. So to understand how the error is confined, how the error is to specify the error is one of a good start. Of course, I will explain later, as in the case of Pompei, there's a lot of uncertainty associated with archaeology. That's also a very different point from modern engineering. There's even more uncertainty on archaeological projects, so that also has to be understood. So looking at reservoirs, this is just basic measurements that it would be good to record. This is quite general, because reservoirs might have an inlet, an outlet, maybe a drainage or a compartment. So definitely it would be good to have, for example, something missing is information about levels. So how the reservoirs compares to the nearby grounds. Definitely, if it's possible, the elevation above sea level. Of course, the diameter of the various orifices or pipes, or measurements of the channels that they are directly close or attached to the structure. Definitely one detail is always missing is the floor slope. It's nothing very relevant in the regular description, but it might have a relevance when you do some analysis. Definitely, the height of plaster. This is also information sometimes missing, because of course the height of the lining will tell you, how much the water, the water level was expected to rise. Definitely details of overflow devices and sluice gate. Normally they're just pictures with some basic measurements, but of course some more details would be useful. Looking at the pipes, ceramic pipes is quite a nice schematic, and the various parts of the ceramic pipes, the various diameters and thicknesses. Again, looking at lead pipes, normally the measurements is made through the minimum and maximum diameter. There's a lot of studies that they mention the minimum and maximum diameter, but it's always good to include the internal perimeter, because that was the way the perimeter was the way the pipe, the Roman pipe, were classed in the various formal classification, like from times classification anyway, was also the width of the sheet, of the lead sheet used to form the pipe. So it's quite useful. And then again, in the case there's the soldering ring has a lot of masses coming into the cross section of the pipe. Yeah, it would be useful to have some information on their size. Yeah, I want to give some more information about, how this engineering analysis was applied in the case of Pompei. That again was the topic of my PhD project. Pompei is quite a wide area, and as many of you might know, the water system presents so many elements, at least the known ones, and we at the moment know only about one top tank connected to the aqueduct channel, the Castellum Divisorium. Finally, the water was distributed through 15 water towers. I added one more because normally there are 14, but already one has been found in the new excavation of Region 5. But I didn't manage to see that yet, but I'm really looking forward. And 30, there are now 43 known street fountains. Oops. And 100 or over 100 water houses are estimated to us connected to the water distribution. So there's many workshops and private houses connected as well. Looking at the water system, there's various hypotheses on the location of the pipes. So this again is the layout proposed by different other scholars, since the main pipes have been removed. Of course, there's no certainty of where they were originally, apart from knowing some stretches found in the various excavation. So of course there are some proposals, but the benefit of the hydraulic analysis, the possibility to validate these layouts or propose other solutions. So that's finally the objective of this research. The point is that we can't, I go back to the previous slide, if we operate in the traditional engineering style, we would start from the very top tank, from the Castellum Divisorio, assign some flow rate and see how those flow rates would distribute in this various layouts, but that would not be a very good analysis, because in fact there's so many unknowns, and again these pipe outlines, they're not certain, so it wouldn't really produce any good information. So what is the best approach, with the one which we adopted, is based on the water demand needed at the endpoints. So the very good deep analysis is to investigate the quantity of water needed in single premises, needed by the public fountains, needed by the baths, and then totalize the water demand of all these local installation from a water tower. So if we assign to each water tower like an area of service, the main purpose of the analysis will be, because unfortunately it takes a long time to develop this analysis with this approach, would be to find out how much water quantity were needed from each water tower. And finally, after that is completed, the calculation of the network and the assessment of the pipeline connecting the water tower can be produced. So looking at the state of the research, I just finished with my PhD to estimate all the supply to the public fountains. I partially estimated the supply to some houses. So this is my next stage of research. There's so many uncertainties, as we were discussing, that need to be taken into account in the engineering analysis. So you can imagine that when you produce some calculation and some estimates, the best the data you input into this calculation, of course, the better will be the result. But in the case of Pompei, even looking at levels, we're now very lucky that Pompei superintendents have made available a chef file with all the points, the elevation points acquired through the piano della conoscenza di Pompei. So basically, there's so many, over 4,000 elevation points with known elevation, so that is of very good use. And for example, looking at water towers, I didn't measure them myself, so I relied on the data published, and I finally chose Olson data because it was most precise. It was obtained through triangulation, because again, when you rely on data published by other scholars, you need to just assess the way it was measured and rely on the bounty on that data. Of course, in any project, you have limits of funding or limits of time, and you cannot assess everything. So in Pompei, there's various types of fountains, built in different materials, but 36 out of 43, they have a little lacus layout. So basically, they are made by stone slab, just a basin built with stone slabs and with just a pipe racing from the footpath up to the split stone. There was an extended survey made on the fountains to find out the dimension of the basin and of the spout orifice, and details of the pipe supplying the fountains. So we just found some fragments with some of the spout orifice, but no pipe is in place, just a fragment in one of the fountain close to the footpath. So after that, the main method used to assess the supply was to estimate the discharge of the overflow channels. So basically, each channel was provided by an overflow to discharge the excess water, and the basin were meant to operate continuously. So we made some assumption that the level of the water in the overflow channel could be like a minimum level, like 1 centimeter over the channel bed, or maybe half the height of the cross section of the full height of the cross section. So corresponding to these water levels, a discharge was obtained. And so for each fountain and each water channel, we found rating curve, which is the curve relating the discharge to the water level. And so that's the main information that we could identify. And to verify this information, then each fountain was connected to the possible towers which were supplying the fountain, and through just lead pipes, but because the diameter, of course, was not known, because no pipe is in place, we had to make a sensitivity analysis. So finally, we assigned a range of variation for all distances, also including the errors, and for all levels and distances, and we found out a range of variation for the hydraulic gradient, and finally for the discharge. So at the end of this study, it was possible to find out for each fountain the discharge of the overflow channel and the discharge of the supply pipe. And finally, I'm just here resuming the average values. So yeah, if you are familiar with this type of fountains, definitely in Pompei, we look at sput orifice like and a supply pipe of around 3.3 centimeters, and then the basin volume in average is less than 1 cubic meter. And the channel discharge as average value was found as a minimum discharge of 0.08 liters per second. The intermediate discharge was 0.43 liters per second, and the full channel discharge was 1.18. As a comparison, I just want to think about your kitchen tap normally has a flow rate of 0.10 to 14 liters per second. So when you is at maximum flow rate, so definitely those numbers, they're quite relevant, and they can be kind of extended to similar fountains, although but and a specific analysis should be needed. But in some time, the lacus of small size, they could be compared to this type of discharge. So where to go next? Definitely, yeah, we can come up with some direction. I want, from my point of view, of course, to suggest to embrace this new approach of the waterfall-based, analysis of the water structure, because of course this is our point of view, which is adding the water and following the flow of water, and definitely is so much needed nowadays to set up multidisciplinary investigation, because any water structure, there's so many aspects related to its building, operation, and modification. So there's so many professionals nowadays involved, and definitely it is necessary to overcome this catalog type of classification of the ancient structure, or specifically the Roman structure. Basically, it's not sufficient to just identify some categories, but looking at the water motion and following the motion of the water, I think new approaches and new identification can be found, and that this can help the matter of terminology. I was presenting 1 year ago about this matter of terminology and how it should be revised as more looking at the operation of the structure rather than architectural details. And definitely following this water-based approach, we might step out of this frontinus based and based interpretation, because there's a lot of, especially not as much nowadays, but in more than 10 years ago, I mean, the standard code for the ancient Roman hydraulic was frontinus, but in the end, it was more and more attested that frontinus test is just possibly limited to Rome, but it's also limited in the proper depth in the hydraulic knowledge of the network. So in the end, is definitely a good reference test, but cannot be extended as a treatise of ancient hydraulics. So concluding, we definitely want to understand and propose modern hydraulics as an instrument for archaeology, but also an instrument to understand the value of the ancient technologies and the lessons that can be found to inform modern engineering. And it's definitely needed to support this collaborative studies through funding and networking, because that's definitely an approach to be taken for future research in this topic, in this field. So I apologize for my first time in this type of online conference. So please allow some deficiency, but I really thank you for your attendance. Thank you.